We will now start talking about magnetic domains. And first of all, I would like to list a few things that are very important for magnetic domains. The first point is that uh, the properties of ferromagnets, such as saturation, magnetization, and remanence, can be explained by a long-range magnetic order. This is within microscopic regions called domains. So the properties of ferromagnets such as saturation, magnetization, and remanence, the fact that we have a remanent field in the remanent magnetization in the absence of a magnetic field, this can be explained by the long-range order. So it's not a nanometer scale order, it's a by long range we mean micrometer scale or millimeter scale, long range magnetic order. And this order is within microscopic regions and we call the long-range order within these microscopic regions magnetic domains. So these are our domains. Okay, so if we look at paramagnets on the other hand, paramagnets do not have magnetic domains because the atomic moments are randomly oriented in the absence of a field, which is due to the thermal energy. The coupling between the moments is too weak. The thermal energy can destroy the coupling and randomize the magnetic moments. So paramagnets do not have magnetic domains because the atomic moments are randomly oriented in the absence of a field due to thermal energy. And when we look at magnetic domains, there are large numbers of atomic moments, typically of the order of 10 to 12 and 10 to 18. These are aligned parallel so that when you look at the magnetization within the domain, it looks saturated. So in magnetic domains, large numbers of atomic moments it's typically 10 to 12 to 10 to 18 are aligned parallel, and because they're minimizing their exchange energy, so that the magnetization within the domain is almost saturated. And if you look at the alignment of the domains, the magnetic moments from one domain to the other, we see that this alignment is determined by certain crystallographic axes, or there can be other sources of anisotropy. And the axis on which these moments are aligned we call the easy axis. The direction of alignment varies from domain to domain and is determined by certain crystallographic axes or other sources of anisotropy that determines the easy axis. So we call the alignment axis the easy axis. Okay, so we have ferromagnets that have saturation, magnetization, and remanence, and this can be explained if we look at the long-range magnetic order within microscopic regions called domains. In contrast, in paramagnets, we do not have magnetic domains. The atomic moments are randomly oriented due to their thermal energies. If we concentrate into a magnetic domain, we see large numbers of atomic moments, 10 to 12 to 10 to 18 moments that are aligned parallel, so that the magnetization within the domain is almost saturated. However, this direction of the alignment varies from domain to domain and is determined by crystallographic axes and other sources of magnetic anisotropy that determines these axes on which the moments will be aligned, that are called the easy axes. So what are the consequences of domains? So consequences of domains. One, these atomic magnetic moments are not canceling each other, they are in permanent existence, so that we get saturation within a domain. Number two, the atomic moments are ordered even in the demagnetized state. So in the demagnetized state, if you look at microscopically what is happening, you see that there are still domains with alignments in different directions. So if you look at the total magnetization, the domains are randomly oriented in the demagnetized state, so that the average value of the magnetization is 0 throughout the sample. Well, having said that, the domains are randomly oriented in the directions allowed by the easy axis, so that would be a better statement. And number 4, when we look at the process that takes us from demagnetized state to magnetized state, it's called the magnetization process. The magnetization process consists of reorientation of domains. So we're basically reorienting them in order to get the magnetization process. Now I want to compare in a 6-moment system the energy, exchange energy of having 6 of them parallel and 1 of them being anti-parallel to motivate the existence of domains. So let's take a look at energy of parallel and anti-parallel arrangement of moments. So I have I'm considering the exchange energy in a 6-moment system. So consider the exchange energy of a 6-moment system. Now we have 2 possible configurations we're looking at. So let's say that these 6 moments are pointing in the same direction. The distance between the moments I call A, of the order of the lattice spacing, and the corresponding energy to this configuration will be the exchange energy in the parallel configuration. And I have another scenario where I have the 3rd moment pointing anti-parallel to the others. So these 2 moments are pointing in the same direction. 3rd one is in opposite direction. The others are in the same direction. And I'm going to call the exchange energy of this configuration the anti-parallel exchange energy. So this 3rd moment, it's the ith moment I'm looking at. If where I is equal to 3, so I'm looking at the 3rd moment. And I want to remember how to write the exchange energy. The exchange energy on the ith moment is minus mu 0, the moment of the ith moment, dot product with sum over j, jij, mj. So it's the exchange constant j that describes the coupling with the ith and jth moment. And within the mean field approximation, so mean field approximation basically sets jij values equal to j. So regardless of the distance between the moments, we have the same coupling constant between these moments. Then I can write the total energy. So the total energy of the system will be E total is equal to sum over I EI, and so this will be equal to minus mu 0 J sum over I MI dot product with sum over J MJ, where I is not equal to J. So I'm looking at the other moments and the interaction with the other moments. Okay, so let me calculate the total energy of the parallel configuration. So I look at the first moment and I see that it's going to be minus mu 0 J. So if the magnetic moment is m per atom, minus mu 0 J m square. minus mu 0 j m square with the second one, the third one, fourth one, and fifth one. So I'm going to do this 6 times. So this is going to be equal to minus mu 0 j. So if I write E1, it's going to be equal to jm square times 5. So it's going to be minus mu 0 j 5m square. So that's for the first one. The second one will give me the same thing, and I'm going to do this 6 times. So this will be multiplied by 6 for the 6 moments. So this is minus mu 0 j m squared multiplied by 6. So that gives me minus 30 m square mu 0 j for the parallel configuration. For the anti-parallel configuration, when I calculate the exchange energy, so I'm going to write for the first moment, so let's do this one by one. I will have minus mu 0 j. I'm going to have m square 4 times, so 4m square, because there are 4 moments pointing in the same direction, 4m square. And then for one of them I will have plus mu 0 j m square. So this will happen for the first one, second one, fourth one, fifth one, and sixth one. So this scenario is happening 1, 2, 3, 4, 5 times. And for the third one, I have plus mu 0 j. It's because they're in the opposite direction. 5m squared, because it's happening 5 times. 5m squared. So the total energy I will calculate here. It's going to be mu 0 j 5m squared minus we're going to have 4m squared minus j, it's 3m squared, so minus 15 mu 0 j m squared. So let me double check this. So for the first one I have 1, 2, 3, 4 times minus mu 0 j 4m squared. Second one I have the same thing. Third one, fourth one, fifth one, and sixth one I have the same thing. And for the first one, the coupling between the first and the third gives me plus mu 0 j m squared. And for the second one, the same thing is happening. Fourth, fifth, and sixth ones, the same thing is happening. So this happens 5 times also. So I will have minus mu 0 j 4m squared plus mu 0 j 4m squared minus 3 mu 0 j m squared times 5. And for the fourth one, for the third one, I have plus mu 0 j m squared, and that's happening 5 times. So this is plus mu 0 j 5m squared. So the end result is minus 10 mu 0 j m squared. So you can see that if you have j value that is positive, so let me summarize here. So I found that for the parallel configuration, the exchange energy is minus 30 mu 0 j m squared. For the anti-parallel configuration, it is minus 10 mu 0 j m squared. So if j is positive, that is positive exchange interaction, you can see which configuration has the minimum energy. Then the energy E is lower for when the moments are aligned parallel within a domain. So this explains why the moments tend to align parallel inside a domain. Okay, so we considered the exchange energy of a 6-moment system. The exchange energy for the ith moment is minus mu 0 mi dot product with sum over j, jij, mj, but jij, the exchange coupling constant, is a constant j for all interactions in the mean field approximation. So I'm using the mean field approximation here. So if I write the energy of the first moment in the parallel scenario, it's going to be minus mu 0 j m squared, interaction with the second moment, third, fourth, fifth, and sixth moment. So it's 5 times minus mu 0 j m squared. And I do this for the first moment, second moment, third moment. So there are 6 moments that will give me the same contribution. So minus 30 m squared mu 0 j. For the anti-parallel configuration, I look at the energy of the first moment. So I'm going to get minus mu 0 j m squared 4 times, but a plus mu 0 j m squared due to the interaction with the third moment. So it's I have minus mu 0 j 3 m squared, and this is repeated 5 times. So it's going to be minus 15 mu 0 j m squared. But then for the third moment, if I write the energy of the third moment, I have plus mu 0 j 5 m squared. So that gives me minus 10 mu 0 j m squared. So I see that the parallel configuration energy is lower if the j coupling constant is positive exchange interaction. So the moments are aligned parallel within a domain.